Welcome everybody to this session on experimental power and why it matters. I'm just going to begin by going over some basics with respect to statistics before getting into the broader question of why experimental power is important and what matters and why we should do something about it when we conduct our research. So let's start with this little example here. Imagine some sort of medical diagnostic test such that 95% of people without a medical condition will be correctly diagnosed as not having that condition. So that gives us what's known as a specificity value of 0.95. So in addition, imagine the test is able to correctly diagnose 4 out of the 5 people who do have the medical condition. This is known as sensitivity, and this value is 0.8 in this case. So now imagine a third piece of information, which is prevalence of the medical condition in the population. So let's imagine that the prevalence is 1%, okay? So we've got these 3 numbers. We've got the specificity, the sensitivity, and the prevalence. So what happens then when we actually give these diagnostic tests to a whole bunch of people? So imagine we tested 10,000 people. So 10,000 people were tested. So we know that the prevalence of the condition is 1%. So we know that of those 10,000 people, 1% will have the condition, which is 100 people. Therefore, 99% do not have the medical condition. So that's 9,900 people. So for the 1% of people, the 100 people that do have the medical condition, we've got a test with a sensitivity of 0.8. This means that 80% of people with a condition are correctly diagnosed. So we have 80 true positive tests. We're going to miss some people. The sensitivity is 0.8. So 20% of our 100 people, even though they have the condition, won't be detected using our test. So we've got 20 false negatives. Okay, so that's for the people who have the condition. Now for the people who don't have the condition, 95% give a true negative test. So 9,405 people give a true negative test because we know the specificity of our test is 0.95. But what that means is that 5% of people who don't have the condition, which is 495 people, actually get a positive result even though they don't actually have the medical condition. So when we kind of add these numbers together, what that means is that of the 575 tests that are positive, 495 of those tests are actually false positives. So the tests suggest that 575 people have the condition, but of those 575 tests, 495 are actually false positives. So what that means is that 86% of the people who produced a positive result actually don't have the medical condition that was tested for. So if you ever think about statistics as being something that's kind of abstract and divorced from reality, think about how statistics are applied in these very particular medical cases where decisions for treatment, say, might be made on the basis of how people's test results come out. So statistics applied to these kind of domains is clearly hugely important. So we really need to make sure that we're understanding statistics when we're applying them to the sort of situations that we're maybe going to encounter in our own research. But also importantly, we can use our knowledge of statistics to better understand data that are reported in journal articles, newspapers, or whatever. So when we think of using statistics in psychology, life sciences, biological sciences more generally, we tend to think of statistics in terms of null hypothesis significance testing. So this is something you've come across as undergraduates many times, I'm sure. Let's take a very basic example. So for a design with 2 experimental groups, we've got the null hypothesis. So this is the idea that there is no statistically significant difference between our two experimental groups. And then we've got the experimental hypothesis, which is the idea that there is a statistically significant difference between the two experimental groups. And what we tend to do when we're running statistics in our own research using the null hypothesis approach to testing, we'll typically reject the null hypothesis if we find that the result of a statistical test comparing two experimental groups gives us a p-value of less than 0.05. So we'll typically adopt an alpha level of about 0.05 and reject the null hypothesis, so reject the idea that there is no statistically significant difference between our groups if the test gives us a p-value of less than 0.05. If we have a p-value of greater than 0.05, we won't then reject the null hypothesis. But it's always worth pointing out that just because a test might be non-significant, that doesn't mean that our two experimental groups are equivalent. It just means that we can't reject the idea that they're equivalent. So it's quite a subtle difference, but quite an important one. So what is statistical significance? I mean, this is kind of, in a sense, a basic question at first glance, because it's something that you've probably been working with right from year one as undergraduates. So let's look at this example. Suppose that a treatment and a placebo are allocated at random to a group of people. We measure the mean response to each treatment and wish to know whether or not the observed difference between the means is real, i.e. it's not zero, or whether it could plausibly have risen by chance. If the result of a significance test between the two groups is 0.05, we can make the following statement. If there were actually no effect, if the true difference between the means were zero, then the probability of observing a value for the difference equal to or greater than that actually observed would be p is equal to 0.05. In other words, there's a 5% chance of seeing a difference at least as big as we have done by chance alone. And it's interesting because when you ask the average scientist to define a p-value, most people actually get it wrong. And if you think about statistics, interpretation and misinterpretation of p-values in the context of open research and reproducibility, you can start to understand why the literature is full of journal articles where results may be incorrectly interpreted, because many times academics themselves have kind of forgotten what p-values can tell us, but importantly, they've forgotten what p-values can't tell us. And it got to the point where in 2016, the American Statistical Association actually had to publish a paper reminding researchers what they can conclude from p-values and what they can't. And it's worth checking out this paper to have a little look at this. So they set out a number of principles on p-values. So p-values can indicate how incompatible the data are with a specified statistical model. P-values do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. Scientific conclusions and business or policy decisions should not be based only on whether a p-value passes some specific threshold. When we think about the sort of critical alpha level of 0.05, that's just an arbitrary cutoff. I mean, what really is the difference of a p-value being 0.049 or 0.051? I mean, it's absolutely minuscule. But if we're choosing to dichotomize on the basis of a 0.05 cutoff, we would conclude that one of those is significant, 0.049 is significant, and one is non-significant, 0.051 is non-significant. But it's just not sensible to create that sort of arbitrary dichotomization at that point. Arguably, proper inference requires full reporting and transparency, and a p-value or statistical significance on its own doesn't measure the size of an effect or the importance of a result. So just because you've got a really tiny p-value, that doesn't mean that you've got a big effect size. And by itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. So when we get on to later sessions, you'll be doing some model building for regression, for analysis of variance, mixed models. And what you'll actually find there is that you can build lots of different sort of statistical models to try and capture aspects of this of one particular data set, and it could be the case that there are many different sorts of models applied to a particular data set will be significant, but you really want to be comparing those models to each other and connecting them with theory, thinking about which statistical models actually make theoretical sense. So in the context of p-values, null hypothesis significance testing more generally, we have to consider what's known as type 1 and type 2 errors. So with a critical alpha level of 0.05, that means we've got a 5% chance of falsely rejecting the null hypothesis. So this is a type 1 error, and falsely rejecting the null hypothesis means that we think we have found a difference in our data when there isn't actually a difference to be found, when it's not there. Okay, so it's thinking we have an effect where we don't actually have an effect. And I guess most of what you've been thinking about in terms of type 1 and type 2 errors as undergraduates has tended to focus on type 1 errors. So thinking you've got an effect when one isn't actually there. But in addition to type 1 errors, there are also type 2 errors, which are kind of the converse of type 1 errors. Type 2 errors correspond to failing to find a difference when one is actually present. So it's failing to find an effect in your data, even though there is actually an effect there to be found. So type 2 errors are critically important. If you have difficulty remembering what's a type 1 error and what's a type 2 error, you'll find lots of different sort of images on the internet that kind of help you learn what is type 1 and what's type 2. So type 1 error is a false positive, thinking you have an effect when you don't. A type 2 error is a false negative, which is basically thinking you don't have an effect when actually there is one present. So controlling for type 2 errors, that should be obvious to you, is actually really important, arguably as important as controlling for type 1 errors. So in the same way that we've got a critical alpha level corresponding to controlling for type 1 errors, we've also got a value, a probability corresponding to type 2 error, which is known as beta. And the probability of arriving at a type 2 error, in other words, failing to find a difference when there is actually a difference there to be found, well, that's related to the experimental power of your design. And for any experiment, power is equal to 1 minus beta. So 1 minus the probability of a type 2 error. Power, experimental power, is a very big deal. So Jacob Cohen in 1992 described why power is such a big deal and what can happen if experiments are lacking in power. So low-powered studies have a lower chance of finding a real effect, and along with questionable research practices that we discussed in the context of open research and reproducibility, so along with QRPs, low-powered studies also have a higher chance of suggesting an effect is present when it's not. And this is one of the reasons why the literature is full of papers that can't be replicated. So the results of a review of a 1960 volume of the Journal of Abnormal and Social Psychology that Cohen conducted at the time, and the results of a more recent review of 1984 volume of the same journal were compared, and it was found that in 1960, the average power of experiments reported in the Journal of Abnormal and Social Psychology was about 0.48. In 1984, which is 24 years later, it was actually 0.25. So experimental power was actually dropping over time. People were running worse experiments in the early 80s than they were in the late 50s, early 60s with respect to designs that had sufficient experimental power. So in 1984, when the average effect size, the average power rather, was 0.25, that actually meant that even though an effect was there to be found in the data, only 25% of the time was it being found because of the use of low-powered studies. And that's a huge waste of money, time, resources in general. And it's as big a problem now as it was then in 1960, and as it was in 1984. So this paper by Kate Button and another one by Norden and colleagues in 2017 kind of looked at, across neuroscience in particular, experimental power to try and determine how big an issue it was for different disciplines within neuroscience more generally. And what was reported by Norden colleagues is that when you look at the different subdisciplines within neuroscience generally, you see that work in genetics, the median power of studies is only 11%. So even though effects are there to be found, only 11 times out of 100 are those studies going to be able to find those effects. Psychology is a little better, it's about 50, but that's still quite low actually. It's not much different from how things were in 1960. Imaging is down at 32. So you can kind of see there's quite a range here, but there aren't any that look fantastic. And what this really means is that a lot of people are wasting their time and energy running studies that basically won't really be able to detect the effect that they're looking for, even though the effect is actually there to be found. So there are different ways of talking about and thinking about power in terms of effect sizes. So one of the, I guess, most commonly used measures of effect sizes is Cohen's d. There are some issues associated with Cohen's d, but it's used quite widely. So I'm just going to talk a little bit about it at this point. So power, which we mentioned earlier, is related to 1 minus beta. So power is actually related to three separate things. It's related to sample size, so the number of observations you have. It's worth remembering that when we talk about sample size, we're not just talking about the number of participants. Later, we'll get on to a workshop on mixed models, where we can kind of think of n as being equivalent to the number of observations. So it's almost not just the number of participants, but it's also the number of observations per participant. So power is related to sample size, but broadly that's related to participants and experimental trial numbers. It's related to the effect size that you're looking for, and it's related to alpha. So Cohen proposes that a reasonable level of power that people should be aiming for is around about 0.8. So that means that, assuming the effect is there, 80% of the time you're going to find it if your experiment is powered to the 0.8 level. And power of about 0.8 with a beta value of 0.2 alongside an alpha level of 0.05 results in a beta to alpha ratio of about 4:1, which Cohen says is a good balance of type 1 versus type 2 errors. And very often in the literature you'll see people talking about effect sizes of different orders of magnitude. Cohen's d defines a small effect size as being 0.2, medium effect size as 0.5, and a large effect size as being about 0.8. And it's important when you're working out how many observations you need in your experiment that what you're actually doing is you're designing your experiment to be powered for the smallest effect size of theoretical interest. And this actually can be a real challenge because many theories in psychology don't say a huge amount about what kind of effect sizes might be expected or predicted by their by their theoretical framework. So it can be tricky to decide what sort of effect size you might be looking for in your research. So you could base your effect size estimate on previously published research, but bearing in mind the fact that previously published research estimates of effect sizes are likely to be overestimates. So you might want to sort of think a little bit then about maybe trying to power your research to detect a slightly smaller effect size than has been reported in the literature previously. So I mentioned earlier that just because we fail to reject the null hypothesis, we can't conclude that that means our two experimental conditions are equivalent to each other. So we need to do other things. One approach would be to work out Bayes factors, go down sort of the Bayesian statistical route. That'll be something that you'll sort of probably come across in the course of your studies. I'm not going to talk about it in this unit. Another approach is to use equivalence testing. I recommend you have a look at this great article by Lakens and colleagues, which talks about a procedure that you can apply to your data to determine whether or not your experimental conditions are truly equivalent to each other. I'm a big fan of data simulation. There are packages out there that allow you to do power calculations, but they can be quite tricky for anything other than the most basic experimental design. So what I tend to do before conducting my own research is actually simulate running, say, 10,000 versions of my experiment. I'll come up with a number of possibilities in terms of the expected difference I expect to see between my experimental conditions. I'll simulate the data over and over again and determine, because I know in my simulated data that I've created an effect there to be found, I can figure out, broadly speaking, or roughly, what sort of sample size or how many observations I need to find the effect that I'm looking for about 80% of the time. So data simulation, I think, is a fantastic way to really get to grips with experimental power. It also means that you can arguably have your analysis script written for your experiment before you've even actually started collecting data in the first place. So data simulation, again, is something that we're going to come on to later. There's a great package by Lisa de Bruin, that's just appeared on CRAN, which allows you to simulate data for different sorts of factorial designs. In addition, there's another great package called SimR, which allows you to do power analysis for generalized linear mixed models via the simulation route. Again, it's really useful to do these kind of simulations when you're before you actually start collecting your data. So it's worth remembering that even when no real effect exists, sometimes we'll think we have an effect. So here's a simulation, set of simulations that I ran. So I ran, say, 100,000 fictitious experiments with n of 25 between two groups within each group. And basically, this is the P curve you'd expect to see if there's no real effect, and it's pretty much flat. But obviously, in the real world, I'm not going to run 100,000 experiments. I'm going to run a much smaller number of experiments. So if we look at what happens if we ran 50 experiments or 50 simulations, we see that sometimes we think we have an effect, other times we think we don't have an effect. If we ran 10 experiments or 10 simulations, so if we ran the same experiment 10 times, well, in this case, a couple of times we'd actually have a significant effect, and we would wrongly conclude that there was a difference between our conditions. Now, the problem here is you can imagine that if you run one experiment and it gives you a significant result, you're not going to immediately assume that that is a false positive. You're probably going to think, oh, I'm going to write this up as a paper now. So it's really important that you actually try to replicate your own results Because if you ran the experiment once and you found a significant result, and ran it again and found a non-significant result, you might start to question whether or not that first experiment was reporting a real effect. It's also worth remembering that real effects will actually not always replicate. So here's a set of 100,000 simulations looking for a small effect size Cohen's d of 0.2. So assuming a critical alpha level of 0.05, we've got a study here, or set of studies here, with about 30% power, which means that 70% of the time we're going to miss the effect even though it's present. So this isn't a great study in terms of experimental power, because even though the effect is there to be found, only about 30% of the time, so this bar here, are we going to find the effect. All these other times we're simply not going to find the effect. So it's really important that we kind of think about type 1 and type 2 error and experimental power when we're designing our studies, so we kind of know what it actually means. Because if we were to increase our sample size, if we went from 50 here to 200, well, with an n of 200, we've got 80% power. So even though the effect is there to be found, and we're finding it 80% of the time, 20% of the time we're not, which again I think illustrates the importance of making sure that you try to replicate your own results. I've always liked the Journal of Experimental Psychology model of papers that would contain maybe 5 or 6 different experiments, and within that set of experiments you'd be replicating the results of experiments 1 and 2 in your later work. So you've kind of got replication built in there, because you're reporting the effect in experiment 1, you're perhaps replicating it in experiment 2, and then in experiment 3, 4, and 5, for example, you're determining the limits of that effect. So it's important to really think about replication, not just of papers that are out there published by others, but replication of your own research. So we have to consider also the issue of sampling bias. When we're taking random samples from a population, some of those samples will be more or less representative of that population than others. Here's a little animation that I did using ggAnimate, where in the left panel we can see a case where we've got a sample size of 20. On the right panel, our sample size is 500, and we've got 2 experimental conditions. I've just called them simple and complex. But if we look at this left panel here, at various points, the distributions of the simple and complex conditions look quite different from each other. And if we look, here, we can kind of, at various, for various, simulations, think that we've got an effect present in our data when one isn't actually present at all, because we can look to see what happens when our sample size increases, and basically across each of our 10 simulations, things are pretty much constant. I think it's number 5 here, where it looks as if we have an effect. And we might, on the basis of that, start to think about maybe dropping the odd experimental trial or the odd participant engaging in questionable research practices to try and make that difference significant. So sample size is important, and we've got to think of sampling error and sampling bias, because sometimes small samples are not representative of the population from which they're drawn. So just to summarize, power is important. Underpowered experiments are a waste of time, basically a waste of your time, a waste of money, a waste of resources in general. And underpowered experiments, in conjunction with questionable research practices and publication bias, ultimately result in a literature that's full of research articles that are wrong. They're reporting results that are not real. The scientific theories or models that you're testing need to allow you to determine what the minimal effect size of interest is, and it's this minimal effect size that you need to be powering your experiment to find. And one of the problems with many theories in psychology is they actually don't formalize or don't really make specific the kind of effect sizes that are predicted that you might find. So it can be tricky actually to work out what the minimal effect size of theoretical interest might actually be. But it's also worth remembering, even in a high-powered study, when you've got 80% power, 80% of the time you're actually going to find the effect, sometimes you'll actually fail to find it, okay? That's just the way it is. And with null hypothesis significance testing, just because you might have an absence of evidence for an effect, this isn't the same as having evidence of the effect not being there, okay? So when our test is non-significant, we cannot conclude the effect is not there. What we have is a situation where we don't have the evidence, we don't have the support to conclude that it is there. And this is one of the common pitfalls in research. If you have a non-significant result, you cannot conclude the effect isn't there. You're just, you just don't have the evidence one way or the other. So that's a very brief overview of a number of issues that we want to consider in the context of experimental power. Hopefully it provides you some broader context with which you can sort of think about your own research that you might be planning. You have to think about experimental power in conjunction with the so-called replication crisis, because arguably a lack of experiment or a lack of appropriate experimental power in research that's appeared in the published literature has resulted in the situation where we have a published literature that contains many papers that are basically reporting effects that aren't actually real. So it's really important that you sort of ensure that the experiments that you're designing are powered for the minimal effect size that you're wanting to investigate.